Hello, welcome to this lecture for numerical modelling for atmosphere and oceans. You have access to the lecture material, these lecture notes and this video before the lecture on Friday, on which I expect you to work through. And on the lecture on Friday, we'll go through the worked examples. You'll go through them with my help. And these worked examples may have some similarity to questions on the exam. So I'm going to start by describing parallel computing. I'm then going to go on to, this is going to motivate the finite element numerical method, which I'm going to describe in the second part of this lecture. So on parallel computers, many computations are done at the same time, often on different processing cores. This is an example of a large parallel computer with lots of cabinets, each with lots of separate processors in. These days there are many different types of parallel computing. I'm going to briefly outline some of them. So the most common that atmosphere and ocean modelers like is multiple processor machines with distributed memory. So that's like lots of separate computers which pass messages to each other, and they all have their own memory. Then there are also multiple processor machines with shared memory, which leads to added complications, because if you're sharing memory, you don't want two processors to change the same bit of memory at the same time. And there are multiple threading. These days, CPUs can do different calculations all at the same time, which makes programming difficult. Vector processing is not done anymore. It's how computing was done in the 1970s and 1980s. So for vector processing, if you have a large vector of data, it gets the same calculation is done on every element of that data at the same time. These were very expensive machines. Then there are GPUs, graphical processing units. And these can be used like very simple vector processors. However, they seem to be a lot more difficult to program for than the vector processing machines of the 1970s and 80s. But of course, in reality, all large parallel computers are a combination of these. So how do we run atmosphere and ocean models on these parallel computers? The most common thing to do is domain decomposition. So this is suitable for multiple processor computers with distributed memory. It's the most widely used form of parallelism for the atmosphere and ocean. The atmosphere and ocean are divided up into regions, and the equations of motions are simulated on each region on a different processor. So you run the same model separately on each processor to simulate the fluid just in that region. Well, of course, they've all got to communicate with each other, although if you divide the atmosphere or ocean up, they're not really separate. So each region has halo regions. So there are overlaps between the regions, and the variables in the halo regions are communicated with other processors. So parallel scaling. As you use more processors, you would hope that the speed of the simulation should increase. So if you divide the domain into more and more regions, you'd hope it's going to get faster. You use more processors, it's going to get faster. Does it? So this is a graph of the speed of a calculation versus the number of processors that you use. So this blue line is what you would like to happen. The more processors you use, the faster it goes. That's perfect scaling. This is this is a graph produced by Nigel Wood at the Met Office, showing the scaling of two of their models. So Endgame is their current operational model, and New Dynamics was their previous model. And this is showing how much they've improved the scaling. This New Dynamics is doing quite badly. So one node here is equal to 32 processors. So once you're reaching 100 times 32 processors, it was really slowing down. It wasn't getting faster as fast as it should do. They did a lot of excellent work on that and improved the scaling. But these sort of numbers of processors still isn't good enough. The modern computers are getting bigger. They're not getting faster, they're getting bigger. And so we need to do better than this. We need to improve this parallel scaling. So some features of the Met Office endgame model. These features are the same as new dynamics. Uses a latitude-longitude grid, uses semi-implicit time stepping, and semi-Lagrangian advection. So I'd like you to think, before the class, I'd like you to think about why these features might contribute to this imperfect parallel scaling that we saw in the previous slide. So here is your task. As well as these reasons, so there are these reasons which may contribute. Think of some other reasons why parallel scaling may not be perfect. Also think why these features may contribute to poor scaling. And post reasons onto the Blackboard discussion site for this module. Also read what other people post. Feel free to comment on what other people post, and you can rate other people's comments. And we'll discuss this during the lecture. So, in order to improve parallel scaling, a lot of operational centres are realising that they need to move away from the latitude-longitude grid and use a quasi-uniform grid. So this is a cubed sphere grid, which doesn't have these poles where all the resolution clusters towards the poles. The problem with this grid is that now the grid is non-orthogonal, so these grid lines are not at 90 degrees to each other. And this means that the numerical methods, the finite difference methods that the Met Office were using are no longer accurate. And so the Met Office are moving to a mixed finite element technique in order to have an accurate model on a cube sphere grid. And with this mixed finite element method, you can achieve similar numerical properties, things like accuracy and conservation, as they could on the latitude-longitude finite difference grid. So in the next video, I'm going to describe the finite element method.